Welcome to episode 1, friends. Basically, the first topic is flat earth versus spherical earth. Listen, according to the first point, Aristotle in his book on the heavens, it is thing about 300 BC, eclipses of the moon were caused by earth coming between sun and moon were spherical. As we observe now also that eclipses were spherical and eclipses is spherical, whatever you say. And at that time eclipses appear spherical. So anyone would think that earth can never be flat. It should be spherical. And this is just first thing. And second point is that sight of the ship, that as we know today that earth is spherical. So whenever a ship comes through the horizon, whenever we see a ship coming through the horizon, first we see its upward part, like this. First we see this part. So how it can happen? It can only happen if earth is spherical like this. It can never happen on a flat earth. Then people started thinking that it might be spherical. Earth might be spherical. Or they started thinking that earth can never be flat. And now come to the third point. Appearance of the pole star. See, pole star appeared a bit high in the northern part than the southern part, according to the sailors of that time. See, suppose this is star, this is star, and this is North Pole and this is South Pole. So if Earth was flat, then the height difference will be zero. So how can this happen that in the northern part it appears high and in southern part it appears low? It can only happen due to this kind of diagram. See, this is north, and this is south. So consider this pole star. There is a difference between height. You see, delta difference. Only if Earth was spherical or another shape. It need not necessarily be spherical, but it should be of some other shape. And on a flat surface, it can never happen. Basically, we cannot blame the people of that time to think that Earth is flat. The appearance of everywhere around them is flat, so they think that the Earth was flat. But now the things have changed. Now we know for sure that Earth is spherical. As we have advanced with the modern science and we went to space, so now everything is quite clear. Let's move forward in the video. Now, according to that time, there is a theory. This theory is especially made for kings of that time. That are we at the center of universe? Suppose you are a king of suppose Roman Empire. So what would you try to assume that I am the king, I am at the center of universe, and everybody is beneath me. So according to that, a scientist of that time, whatever his name, Ptolemy, in first century added, he proposed a theory that Earth is at the center of universe and all the planets and sun revolve around in circles. The idea was accepted because of the heaven hell. See this on this, that this is Earth, this is planets and sun, and outside the observable universe there is heaven and hell. So that's why the idea was accepted, because it suited the king at that time. But there is one advancement in this idea, that a spherical model of universe evolved at that time. And this is a very quite observation. And this idea has one obstacle, moon's path. If this idea was true, then the moon's path observed by that time of people will create an obstacle. We will see how in next slides. For now, let's move forward. Now come to the best part. Brave Nicholas. The topic is the brave Nicholas. Nearly 1500 years after a priest called Nicholas Copernicus put the idea forward that the sun was at stationary center and all the planets revolving around in circular orbits. This idea is quite good, but let me tell you that he did not publish the idea directly, because if he did, then the king would directly slaughter him without a single doubt in mind. Yes, he anonymously published this theory, and everything went. And I don't know how the current scientists, or current historian scientists, discovered that Nicholas Copernicus did this, because he published his theory anonymously. Well, that's the case for them. So let's move. Now comes my favorite scientist, Galileo. In 1609, he started observing universe through a telescope. And let me tell you, he's a very great scientist. And he started observing universe through his own handmade telescope. Let me tell you how. Because see, at that time telescope was invented, but he does not have the money to buy it. So he buy the procedure. He somehow he wrote a letter to the someone, and they gave him a procedure to build a telescope, and let me tell you, he built a very advanced telescope to observe the universe. And if you are in 11th 12th or you have read optics, you may know about Galileo telescope, how it works. So he started observing universe through his own telescope, and he found very interesting things. When he looked at planet Jupiter, he found moons of Jupiter, and that was a remarkable beginning of the universe. That was a remarkable achievement, or according to that time. And here comes a great scientist, whatever you call. I know how he did that, Kepler the Great. But he did that. He suggested that Copernicus suggested that our orbits were circular, but he somehow did that. Somehow what? He observed the universe through his whole lifetime, and then he suggested that the orbits were not circular but elliptical orbits. And according to that time, physics on the magnetism were somehow little bit developed. So he says he thought that the solar system was held together by some magnetic forces, which indeed some bit true. That is not magnetic, but it is gravitational. We will see that in next slide. So let's move. Now here comes the great Newton. Newton, the Principia Mathematica Naturalis Cos in 1687, the most important writing in the history of physics, maybe after Einstein only. In his book, he put forward a theory how bodies move in space-time. How bodies move? A force equal to mass into acceleration. Not only that, that's how body move. That's what he written in his book. Not only theory, but he developed mathematics to analyze that motion, that we call the calculus, that we have to study in school, and it's so boring. Basically, he said that the universe, in every body in universe, attracted towards everybody through the force called gravitation, and that force depends on inverse square of their distance between them, mass, and that another's body mass, and it is basically equal to force equal to K m1 m2 upon r square. And what is K? K is gravitational constant, as you know. So let's move forward in the slide. I will tell you that elliptical orbits were possible. Basically, let me tell you how elliptical orbits are really possible. See, circular orbits were possible if this is what I think, that if only Sun and Earth were present, but there are Jupiter, there are Mars, there are Mercury. There somehow the forces may settle and the orbits will become elliptical. So that's how he explained elliptical or concept of elliptical orbits. But he made a big blunder. That Newton's theory raised a big problem. If each body will attract each other, then eventually every body will collide and universe will be destroyed in a big explosion. Suppose me and you are attracting each other. Eventually, if we do not move, then after some time, a long time, we will eventually collide. So this is how it should go with the whole universe. That everybody should attract toward each other and everybody collide each other and whole thing explodes. Everything got destroyed. Boom, everything got destroyed. So how this is a big problem. So how we manage to solve that? So how universe is still alive? How then? How? Basically, Newton's friend, he said that Richard Bentley in around 1691, that universe is infinite. So there are infinite number of bodies, infinite number of stars, suns, moon, planets, and it is distributed throughout the space, throughout infinite space. So there is no center. Where infinity has basically no center, and you know that. So universe will never collapse at its center. But how can we assume that universe is infinite? This idea falls miserably due to that. Let's see the next point. And to solve this problem, they eventually came up with a very bizarre idea, very strange idea. I don't know how would I come up with that. That the gravitational force behaves as an attractive force at small distances, like the distance between Earth and Sun. I am talking about astronomical units. In astronomical units, the distance between Earth and Sun is very small, and gravitational force attract as repulsive forces at large distances, like between two galaxies. It will let me tell you this, maybe one galaxy distance between two galaxies maybe 3.4 light years, 3.9 light years between next galaxy and Andromeda galaxy. So the gravity will act as repulsive forces at that distances. Then how it solve the problem? So see, attractive forces between two objects will balanced by the repulsive forces. So let me tell you how it works. See, suppose this is the bodies at small distances, and this body will put a force on this body. So this body will never collide with this body, and this body will put a force on this body. So this body will never collide with that body. So eventually the model is static. So nothing moves, and only if we put some external force, then only it moves. That's what Newton first law said, that if we put an external force, then only bodies in uniform motion will move or behave out of their behavior. So eventually the static model of universe came to reach that everything is static, which is Newton's first law, that everything is static unless some external force is applied. So universe is static. They said this. Here's a problem, that for the current time, if you study little bit now, then you know that universe is expanding. That means then let's know how it came in mind. Till 1929, the static model of universe, in fact, Einstein believed that universe was static. When he discovered his general theory of relativity, he added a cosmological constant because his theory was that great, no? That without discovering him, the that universe was expanding. He already his equations were showing that universe was expanding, but he think that is static, so he added an extra constant to that equation, so the equation will become compatible to current to observable scenario. Basically what are equations? Basically first you form the equation and then try to modify the equation according to the observable scenario. That's how equations are great equations are built. Let's see that what is Einstein's great equation. Let me tell you how he is great. See, this is his equation. RAB. This is a tensor. I will tell you what is tensor, but in the upcoming videos. It describes how the curvature changes from place to place. And this term here, half of RGAB, these are all metric tensors, I will tell you, defines distance in curvature. Distance. A space is curved. And this guy here is mass energy, content of that space. And here is that famous cosmological constant. It shouldn't be here at that time, but this equation was discovered like that. This cosmological constant basically refers to that repulsive force. I told you, that in previous slides that repulsive forces at large distances gravity behaves, whatever. So let's move to the last point of my video. In 1929, Edwin Hubble telescope, you know that, na? Discovered galaxies are moving away from each other. I will tell you how he discovered that. Let me give you a hint. He discovered through the red shift. I will tell you in upcoming episodes. So he thought universe is expanding and the Big Bang concept of Big Bang begins, and which is ruling till the world now. This is current universe. This is accelerating expansion. Universe is expansion. Here the Big Bang begins. So this is how we reached from 1500 or say 300 BC to 1529. This is 1929. This is the development of models of the universe. So I would say 300 to 19, 2000 years. Yes, that 2000 years we break our minds. So we reach this theory. This is certainly pathetic for the humans that 2000 years we take to discover this theory. But what we can do? The technology at that time or the human thinking at that time were too low, and now we are developed quite that we are discovering new things every day. I will also make an episode that how we are discovering new things every day in upcoming times. But for now, let's end this video, and episode 2 will come very shortly. So goodbye. Take care. See you in next video.